Hello everyone, today we are going to explain Ethernet frames. Now when we talk about the data link layer, all the data that reaches this layer will be encapsulated. In this process, let's say we have a switch here, and this switch is connected to many PCs. If we are dealing with internal company traffic, then if the data is encapsulated, we need to encapsulate it into an Ethernet frame. So how did Ethernet come about? We say that everything encapsulated at the second layer is called a frame. Many people have always been unclear about what Ethernet is and why it's called Ethernet. So we say that once the data reaches the second layer, we need to encapsulate it. And after encapsulation, it's called a frame. When defining the term frame, scientists discovered that light can actually carry data. Therefore, they believed that light should have a carrier. At that time, the carrier for light was set as ether. Ether in the earliest days was defined by scientists as a type of substance. Just like air and water are nouns for substances, ether is a substance, but we seem to have never heard of anything called ether because we haven't found it. They believe that when light is transmitted, it should have a carrier called ether, just like us. When sound is transmitted, everyone thinks it should have a carrier. If sound needs air to propagate, they believed that a substance like ether was helping light to transmit signals, and such a network was called Ethernet. However, later we discovered that light transmission actually does not require any carrier, but this substance had already been defined. Once it was defined, it was simply not retracted, because retracting it would be quite awkward. So, this term was adopted and we called it Ethernet. Although we never found this ether thing, the name was already given. This is why, within a network, if we use layer 2 for encapsulation, we choose between these two formats. So, this frame, regardless of which encapsulation format I use, is actually called an Ethernet frame, referring to its name. Here, whether it's E2 or 802.3, they are both Ethernet standards that help achieve encapsulation within the entire network scope. For network communication, you can understand it within the scope we currently see. All network interfaces, whether it's a network cable or fiber optic, are actually our network interfaces, and these network interfaces are all part of the Ethernet standard. Unless in the future you are working with an ISP's wide area network, then we would consider encapsulation under the wide area network, which is a separate matter. Here we discuss why two types are defined in this process. First of all, the 2 is the upper type, and 802.3 is the lower type. You can notice that the lower one is overall longer, meaning it encompasses more functions. In this part, and our part here, it actually refers to some parameters that I can now add. It adds a bit more, while the upper one adds a bit less. Let's first take a look. Do you think it's better to be longer or shorter in this context? Actually, in this context, shorter is better, because future data interactions emphasize quick transmission. When it comes to data transmission, we prioritize speed. If the data above is encapsulated layer by layer, we first go through 4 layers of encapsulation, encapsulating its original port, then through 3 layers of encapsulation for its original IP, and finally through 2 layers of encapsulation for its original MAC. The upper layer data. After multiple layers of encapsulation, the knife falls to the second layer. Here, we say just one was added. If we choose the encapsulation format below, we added a bunch. So there's less of this thing above and more of this thing below, making the one below possibly more powerful. It's just like when we cook, there are many seasonings inside, which definitely makes it more delicious. If we add fewer things, the packet is smaller, and during the entire network communication process, the transmission speed of the packet will be very fast. However, if I keep sending packets to the other side continuously, and each packet has a little more than the other side, before sending, I have to add a little more to each one, and when it reaches the other end, it has to unpack a little more, so it will be slower. In this context, we often choose to encapsulate using the E2 format. However, whether it's encapsulating in the E2 format or the 802.3 format, actually it doesn't concern us network engineers. This is determined by the developers at the initial design stage, deciding whether the current protocol or application will use E2 encapsulation or 802.3. We just need to understand this format. So let's start with the FCS here. Why start from here? Because this involves a very important function of our data link layer called error detection. Suppose I'm sending data from A to B, and if during the transmission process it gets corrupted, B can discard this data. But how do I know that there is an issue with the data? It's through the FCS, the frame check sequence. If we later forward the data, it will be based on an algorithm within this frame check sequence called CRC. CRC, cyclic redundancy check, is used to verify the entire information, meaning it checks all the content in this part. Apart from the FCS field, we will perform a check on all of this. Through this CRC algorithm, you just need to know that before the data is sent, it will preemptively check the preceding data using this algorithm and calculate a value. For example, if this value is X, we don't need to worry about what kind of algorithm or formula it is. When we send data in the future, we will send it along with this value. Alright, so if I send this data, now it will carry this FC value. So here, didn't it calculate an X? Alright, I will fill in the value of this FCS's C, placing it into the FCS field. Through CRC, using this algorithm, I calculate this X and fill it in, sending it along with this X. Later, when it is sent to the other end, we actually send it along with this X1, carrying all the information together. After it is sent to the other end will also calculate it using this cyclic redundancy algorithm. For example, if a number Y is calculated, we will compare it. If these two values are equal, it means the data is correct. If my X and Y are not equal, it indicates that there is an error in the data. For example, if my X is 2 and Y is also 2, it proves there is no issue. If my X is 2 and Y is 3, it proves there was a problem during the transmission process. In this context, these bits are actually transmitted in the network in a 0101 format. If any of them change, or if the FCS changes, regardless of which one changes, the final result will be unequal, indicating a problem has occurred. There is an issue and our device will discard it. This is similar to if we want to send some packages to good friends to mail some things. Suppose we send some candies. After weighing them, we counted and found there are 66 candies. We then wrote a note along with the candies and our items. 66 notes, I pack them together with the package and send them over. When the recipient receives it in the future, your friend will also need to check and count the candies. Then finally, they open the note to see if you wrote 6666. If they count 66 as well, it means nothing is missing, and they will accept it normally. However, if now they find 61 when counting, but the note says 66, then 5 are missing. In this case, they will think, oh, there's an error, and they won't accept it. Or if they don't see the note inside because it was lost, they will also assume there was an error in the process. Once an error occurs, they won't accept it. Previously, we mentioned to everyone that during data transmission, we perform a check, to see if there are any issues. If a piece of data is sent to the device you're connected to, and if you make a mistake in the first step, is it necessary to go through our ISP and so many networks to reach the other end? It's not necessary, right? The packet can be dropped in the middle. In this context, we say that once the FCS, frame check sequence verification, is successfully completed, we hand it over to the upper layer for processing. However, there are many protocols at the network layer, which you might encounter in the future, including those we discussed in previous courses, or IP. They are all protocols at the network layer. So how do I specifically send a particular protocol to the upper layer? Or in this context, for example, when we transmit some data. Regarding this data, it might seem quite straightforward to everyone, but when we transmit it over the network, it is all sent as a binary bit stream like 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1. When it reaches the other side, the recipient begins to read it, and upon reading this part, they understand, oh, this is a layer 2 encapsulation. Once that's read, doesn't our upper layer still have a lot of other content? This means that when I read this content, I need to know, oh, when I read this bit, what exactly is it? Specifically, this bit is the destination IP and this bit is the source IP. I need to know what they are and how I should interpret them. In this context, if you want to know what form our upper layer takes, here we have a type to identify how you should read the upper layer in the future according to certain rules. If it's in 802.3, we use the length to represent a length. This indicates that when we read up to this point, we can choose between two standards. We can interpret it as an E2 type or as an 802.3 length. So how exactly do we read it? Actually, for our layer 2, we don't consider this issue. In fact, before data transmission, there is an issue called the preamble, but this is not a concern for us network engineers. It has nothing to do with us. So you might find that when reading digital data, you suddenly don't know how to proceed. When you reach layer 2, you think, now I need to start reading layer 3. In this context, at layer 3, we might learn about 6. But what exactly is encapsulated here? In this context, if our packet structures are all the same, for example, if I have gear 1 delta 110 here according to the ARP reading method, it has one meaning. According to another reading method, it has one meaning. And according to the IPv6 reading method, it has another meaning. So, in this context, when we say at the very beginning of encapsulation, during this process, the data must be encapsulated according to this tab to identify our upper layer protocol. Go tell you what format the upper layer should follow when the other party is dismantling in the future. We won't discuss the data here, just that our data is in here. Data. Encapsulation involves 4 layers, encapsulating the original log's I port number, and 3 layers encapsulating the original log's IP. Finally, it reaches the second layer, E. Actually, after these layers of encapsulation, we refer to all of it as data, CAUX. Now, in this context, we say there is a first MAC here called the destination MAC, which means I am now heading to a town. Destination. Its MAC address, which we call the destination MAC, is unique to each device, having its own MAC history. Here, physical address, MAC address, and hardware address all refer to the same thing. If, during this process, a computer wants to communicate, it must have a network card. And that network card, each network card actually needs to have an address. The MAC address here is factory set and globally unique. It is burned into the chip and does not require us to configure it. In an Ethernet network, it identifies the position of the device on our link. For example, where are you connected on my link? This switch might connect to many devices in the future. For instance, here is a switch, and below it, there are many PCs. If the PCs want to communicate with each other, they need to do so through this switch. For example, now within this setup, I want this switch to help PC 123 achieve communication. Suppose PC 1 wants to communicate with PC 3, and I want to communicate with it individually. Then we need a unique name. For instance, if everyone in the class is looking for Jack, not all 68 people can be called Jack, otherwise it would be impossible. To accurately find the person you want to find, in this context, in the future. In this process, the switch will use what is called a MAC address table to assist in forwarding. So, in this context, communication between 1 and 3 is also achieved by finding it through the MAC address. This MAC address is unique, and you can find it directly. This is the basic form of communication we are talking about. Now, if I have some data and I want to send it to PC3, then PC1 has a network card. For example, if its MAC address is A, PC2 has a network card, and it is 10B, PC3 has a network card, which is just C. So here, if PC1 wants to send data to PC3, when it sends it, it will write that my source MAC is A, and the destination MAC is C. Then, when it reaches the switch will know, oh, you are looking for C. So here, the original MAC address is the sender's MAC address of the data generated, called the source MAC. If you want to find someone, the destination MAC address is our C. When sending from A to C, when I generate data, I need to use this destination MAC and source MAC to identify who is the recipient of my data. Who is the sender of my data? This is the source MAC address. So what about the destination MAC address here? It belongs to the receiver, meaning who am I sending this data to? These are the types and significance of the E2 we mentioned above. The source MAC identifies the recipient of the data, and the sender's information are. The type identifies the upper layer protocol, and the data is our actual data. Inside there might be real data, along with our layer 4 encapsulation, and then layer 3 encapsulation on the outside. For our layer 2, this whole thing is considered data. Additionally, we have our FCS, the frame check sequence, which uses a cyclic redundancy check algorithm. Verify whether there are any issues with the overall information during this process. This is our E2 format. Based on the E2 format with these 4 parameters, GIL, we can actually implement a function of our data link layer here. In fact, the data link layer has 2 functions. The first is to complete, error checking during data transmission. The second is that I can provide information on the link through FCS, or PREAM, and then, using our original MAC address, we can actually complete the basic format of our data link layer in this process. So, E2 can achieve transmission here. But why is there also an 802.3 since E2? It can perform the function of the second layer and also verify the MAC address, allowing me to discard problematic data. Why is there another standard? It's because E2 has an advantage that I've mentioned before. It is relatively simple with less encapsulation. It only involves these 4 parameters, our pipe. Once these 4 parameters are encapsulated, we can send it directly. However, its biggest drawback is that its encapsulation is overly simple. Although we say that the simpler the data transmission, the better. But what if we want to develop at the data link layer? If I want to develop some new features, for increasingly complex networks in the future, the simplicity of E2 will present a problem. That is to say, if manufacturers now want to develop some proprietary features, our TAP can only identify some public protocols, and it cannot support some of our proprietary ones. For example, in the future on Huawei devices. We will learn about a private technology called this. Once we involve these private technologies, in the type field, it cannot be identified. If every manufacturer wants to develop some new features, then the public features, it is not possible. In our case, within this, outside of development, I will develop a bit of private, meaning it does not support private. However, in this context, actually most of the protocols established by TCP/IP are used publicly. Public means that this thing is free. Free and easy to use with strong compatibility. Many new technologies are actually proprietary technologies of manufacturers, and based on this type, it cannot be indicated, which is its limitation, so we can only switch to public use to use the technology. But if we want to develop new features, we have certain limitations. Firstly, 802.3 can support some private protocols. Secondly, there are also some public protocols here. But the encapsulation they use is also 802.3. For example, why does a public protocol like STP also use 802.3 here? Because if I involve some control functions, then this type, it's too simple and cannot provide adequate support. So here, if it's a public web protocol, most of the time it's type. If it's a public protocol with strong control or a private protocol, 802.3 will be chosen. Now let's take a look at what is inside 802.3. First, the length here indicates the size of our upper layer data, which is the length of the data part we have now. There's also something called LLC, which stands for Logical Link Control. It has several key points, but you don't need to memorize them, just understanding is enough, because when it comes to knowledge, it's not necessary to know every detail thoroughly as it's not needed. First, within the LLC, there's a parameter. What is this place called? It's called DSAP. Now, what is this DSAP used for? We need to know that this DSAP is called the Destination Service Access Point, which is similar to saying what kind of protocol your upper layer wants to use. It is actually equivalent to, you could say equivalent to the P in here. The type in E2 now in this process, this is DSAP, and there's another called SSAP. So what is SSAP used for? It's called the Source Service Access Point, which is the service I initiate locally. In theory, the data for DSAP and SSAP should actually be equal. For example, in the future, I might use a technology on my device called the STP protocol. I use my local STP to access the peer's STP. Here, it shows which service is generating the data I am currently producing. Then, what do I want to access on the peer side? In this context, SSAP in our E2 does not have a tap, whereas DSAP is similar to type. Now, in this context, if we look into the future, you will find that DSAP and SSAP are often equal. So, basically, when people capture and examine data packets in the future, they will discover that there is actually another parameter called control. Control here represents control, and originally, 802.3 intended to define a field. To perform some control at the data link layer, but it was not developed. Initially, there were many ideas and attempts to achieve certain functions. However, in the end, it was found that it couldn't be done. So this is the situation. So this field, being too complex to develop, resulted in the crawl field not being used. This field is always a fixed value, BISO 3, and it does not change. Because it has already been developed and released to the market, it is used as is and kept just in case it is developed in the future. Often, the things we develop are generally only added to, not reduced. Because in the entire internet communication field, I don't know how many of you have heard this phrase during development. If you find that the environment can run this project, this software can run. Even if there is a bug, do not change it, because fixing one bug might lead to more bugs. In other words, if everything is fine now, but you delete some fields due to your input, leading to new problems later, that would be bad. Now, in this context, our LLC can handle this. Besides this, we also have Snap here. Snap has two parameters. What do these two parameters mean? This Snap is called a sub, Network Service Access Point. We say that future privatization actually relies on this, privatization. If it were public, this parameter would not appear in our network. Earlier, when we talked about E2, we mentioned that if developers or manufacturers want to create some mesh protocols for their own manufacturers, E2 cannot be extended or defined. However, 802.3 has reserved this field in advance. This means it considered that manufacturers might develop some privatized protocols, and only when manufacturers use and develop these privatized protocols, then the snap field will be activated. If it is activated in this process, the manufacturer identifier will appear here. You can understand it as an organization identifying different institutions, and it is different. In this process, there is also a type here called PID, which means that for manufacturers, I might have multiple private protocols, and I also create an identifier. Similar to the protocol label at our upper level, this will identify which label or private protocol of the manufacturer it is to market. And in this context, if I am using a private protocol here, then in the previous LLC, the DSAP and SSAP will be fixed as ours. 0xAA represents no value. If you read this 0xAA, you know, oh, this is a private protocol, it is not a public one. If it is not 0xAA, it means it is a public one. It's like a switch. If it is 0xAA, then there will be snap here. It indicates that it is a private identifier, specifically specifying which manufacturer's specific private protocol it is. If indeed within this LLC, the DSAP and SSAP are not R0xAA, then it means it is a public protocol and this value will not appear in our packet. So here, everyone should know that whether it is a public or private protocol, you should understand that the second layer can actually handle and encapsulate it. Nowadays, E2 is used more frequently, but if it involves privatization, 802.3 will be used. Of course, some public protocols also use 802.3. However, E2 is still used the most because it is relatively short. And during this process, We will use this to carry out a series of identifications or guaten. Here we can see this B. What does this B mean? I might have explained it before, but you may not remember it very clearly, Ma. This B stands for beta, which means byte. Now, when we say 1 byte, it equals 8 bits, 8 positions. So, what about a binary number? It equals either a 0 or a 1, so 8 of them. V equals 8 binary numbers. In this context, 6 bytes represent 48 bits, from which we can deduce that a MAC address, the original MAC, is 48 bits long. This is the length of a MAC address, mazhua. In this process, when we encapsulate in the future, if we encapsulate based on E2, the data that our upper layer can carry is 46 to 1500 bytes. If we use 802.3, it is 38 to 1492 bytes. In this context, if we encapsulate too much at the data link layer in the future, it will affect the length of the upper layer data. If it is E2 here, in this context, there is less to encapsulate, which is more advantageous. The data will be transmitted a bit faster. In this process, the less we encapsulate, the faster it will be transmitted. Here, whether our data passes through the transport layer, the data link layer, or the network layer, as long as it reaches our data link layer, it is considered upper layer data for us. For upper layer data, we actually have requirements regarding its size. We will transform the data into uniform sizes, so that during transmission, the data sizes in the network are roughly the same. This helps us achieve more fairness and allows for faster data forwarding. In the forwarding process, there is a value called MTU, which stands for Maximum Transmission Unit, describing this aspect. A range refers to the data reaching my data link layer, where the maximum size is defined. The layer 2 encapsulation refers to this segment where we encapsulate this data. The maximum is 1500 bytes. You see, if it's Ethernet 2, we encapsulate fewer things, so the maximum can be 1500 bytes here. However, if it's 802.3, we encapsulate more things, which will occupy some of the data itself. Occupying some of its content means that the things I encapsulate here will be a bit less, and it will squeeze some space from the upper layers. This is based on my current definition that when our data reaches the data link layer, its size is fixed, meaning the maximum is 1500 bytes. In addition, the outer bytes total 18 bytes, making the maximum 1518 when combined, which is fixed, similar to our MTU value. If we want to add more parameters at the second layer, we won't expand the MTU, so we have to do it here. We need to use some of the parameters within this part. In this process, our minimum transmission is 46 and the maximum is 1500. Here we ask why the minimum is 46. Because in this process, it actually originates from a very old standard we used before, involving some algorithms. But everyone should remember, in the future, our data must be at least 46. If the data is less than 46, for example, just 1 byte, what do? Then I will fill the rest with zeros as a padding patch, making it up to 46, and then upload it. These are the two formats of our data encapsulation. If anyone wants to learn Huawei certification technology or obtain the Huawei certification question bank, please send me a private message. I can also leave more comments below the video for technical exchanges.